So let's look at two things dealing with equilibrium constants. Calculating an equilibrium constant. And that'll be calculating equilibrium constant. Then this will be the easy way. And then we're also going to look at a slightly harder way that requires us to use implied information. Information hidden in the problem to answer the question of what the equilibrium constant is. More typically, though, what we care about is not calculating the equilibrium constant. We can often look these up off a table. And because we can look these up off a table, the real question is, use the equilibrium concentration, use the equilibrium constant to predict concentrations at equilibrium. So this is more common. Let's take a look at calculating equilibrium constants. Let's take a look at a problem, a very typical one. At equilibrium, the reaction below has the following partial pressures. What is the equilibrium constant for the reaction? Pretty simple, pretty straightforward in terms of the behavior of a system. So we have N2 plus O2 going in equilibrium with NO2 gas, NO gas. These are all gaseous. And we're given our values in atmospheres. And we can use those values to determine the equilibrium constant. Once we know the equilibrium, we can just use Kp in this example. Though Kc would also work, Kp is probably more beneficial for us because it's all set up. Again, it's going to be approximately products over reactants. Approximately products over reactants, and so that'll be NO squared divided by the partial pressure of NO squared, all divided by the partial pressure of N2 times the partial pressure of O2. Again, once we have this, we just plug in our respective values. And then a little calculator magic. Get 5.05 times 10 to the minus 2 molar. Sorry. 5.05 times 10 to the minus 2 as our equilibrium constant, Kp. Pretty trivial. Given equilibrium concentrations, it's just plug and chug. Let's take a look at a slightly more involved version. A 1 liter sample of pure phosgene COCl2 has a concentration of 2 times 10 to the minus 2 molar, and it's allowed to reach equilibrium. At equilibrium, the concentration of CO from the equation below was found to be 7.5 times 10 to the minus 3rd molar. What is the equilibrium constant for the reaction? What we see is the following. They give us two very different conditions. They talk about the CO and they talk about the phosgene COCl2. And so we can set up our equilibrium constant. And Kc in this case will be equal to COCl2 divided by the concentration of CO divided by the concentration of Cl2. Unfortunately, we're missing a bunch of information. We're told the CO concentration at equilibrium. So that's good. We can use that to tell us to plug in there. But what about the Cl2? What about the COCl2? I mean, we're told something about the phosgene. We're told that at the start it's 2 times 10 to the minus 2 molar. But we don't know what it is at equilibrium. We only care about equilibrium concentrations. So how do we find it out? Well, as it turns out, we have a lot of information in this problem. And we just have to use our chemical knowledge of what goes on in a reaction. So if we just strip out the information from the reaction, what we see is we start with nothing but pure COCl2. And then the reaction drives backwards to form CO. And we know how much CO was formed. So we know this. What's implied in the knowledge of that the CO is formed is that the implied information, here's where it gets hard, is that how much chlorine is also formed at the same time. How much Cl2 is formed at the same time. Now, we can sort of think about this algebraically. We can talk about CO and Cl2 and the COCl2 in an algebraic form. And we can say that, well, okay, whatever the initial concentration of COCl2, stoichiometry says if we lose some of the COCl2, for every one COCl2 that's lost, we gain one chlorine, and in this case, one CO. We can express this algebraically. At equilibrium, the COCl2 concentration will equal whatever was consumed. Another way of looking at it would be the initial amount of CO minus whatever was consumed will equal the initial amount of Cl2 minus whatever was consumed, initial amount of COCl2. Well, they tell us what the equilibrium concentration of CO is. They say that it is at equilibrium, and there was none to start with, we will get 7.5 times 10 to the minus 3rd molar. That means that the amount of chlorine also has to be 7.5 times 10 to the minus 3rd molar. For every one COCl2 that's consumed, you will get one Cl2 and one CO. We know how much CO is formed, so they're the same. Same can be said for the COCl2. We know that we start with 2 times 10 to the minus 2 molar. If we subtract out that which is consumed, which in this case is 7.5 times 10 to the minus 3rd molar, that will give us the concentration of COCl2 at equilibrium. Or, in this case, 0.0125 molar COCl2. So this would represent the concentration of COCl2. This would represent the concentration of Cl2, and this would represent the concentration of carbonyl. Once we know all these, it's a simple matter of plugging them into the equation to get our equilibrium constant. In this case, 0.0125 molar for the COCl2, all divided by 7.5 times 10 to the minus third. I'm just going to square this since they're both the same. This will give us the value. So we have to use the implied information from the stoichiometry. The amount of products consumed is not independent of the amount of reactants formed, or vice versa. Like the two quantities are tied together. Now, I'm going to offer a tip. So let's take a look at this. A plus 2B goes to 3C plus D. All right. Let's talk about expressing these quantities algebraically. And the tip is use the stoichiometry. So here's our equilibrium expression. Our equilibrium expression would be K would be equal to D times C cubed divided by B squared times A. So this would be the algebraic expression that would encapsulate that particular equilibrium. Now, we're going to just say, we're going to just say everything, all of the concentrations before equilibrium are the same. A will equal B, will equal C, will equal D in this case. We're just going to set those all equal to 1 molar. This is just an example to make things clear. Regardless of which direction the reaction proceeds, we can choose one, pick one, A going to B, the reaction going forward, or the reaction going backwards. It doesn't matter. Mathematically, it will all equal the same number when we get to the end. Let's generate an algebraic expression that describes what the heck is going on for the concentrations at equilibrium. So what about at equilibrium? How would these look? So let's take a look at A. If we just define A as whatever its initial concentration is, whatever its initial concentration is, I'm just going to call it A initial, little subscript. Whatever its concentration is, when it's consumed, we'll just call whatever is consumed, we'll just define it as X. Whatever X is. X is just some variable. How much B would be consumed? If 1A was consumed, how many B's would be consumed? It'd be twice as much because the stoichiometric. So we could say B initial, whatever would be consumed would be minus 2X. At equilibrium, we can also talk about C. Well, C, notice this is a product. So for every 1A that's consumed, we generate 3B. So where this is a negative sign, this would represent a positive sign, plus 3X. And similarly, we could say for D initial, whatever it is, would be plus X. Now, you could do it relative to C or relative to B, but for sake of simplicity, I highly recommend that you just stick with the stoichiometry. Plus, it allows you to check very easily. If you know any one of these quantities, any one of the changes in the quantity X, you can figure out all of the other ones because they are not independent. And so this can be plugged into our algebraic expression. And if knowing k, a init minus x, we could generate a more algebraic expression for this. D plus x will equal, no, not equal. C plus 3x cubed divided by b minus 2x squared a minus x. This would be a complete algebraic expression that would represent the change. So given any initial concentration and any final concentration, we would be able to plug in the correct values. Stick with the stoichiometry. It makes checking things easy. This would imply 1, this would imply 2, 3. And again, this represents the change of the respective amounts.